Hello and welcome once again, students. This will be part 2 in the series of videos for your chemistry class 12. In this series, we started the very first video discussing about the general properties of group 16 elements. And so far, we have discussed oxidation states of group 16 elements. We will continue our discussion from where we left off in the previous class. So let us begin today with a question. Okay? And what is that question? That question is, OF6 does not exist, but SF6 exists. You have seen similar questions in group 15. For example, we discussed that we cannot have NCl5, but we can have PCl5. Right? In a similar sort of way, in this chapter we are discussing that we cannot have OF6, but SF6 exists in nature. OF6 we cannot prepare, SF6 we can prepare. Why is that so? Why is that so? That is because of the thing that we learned in the previous class, oxidation states. Okay, oxidation states, the availability of vacant d orbitals. That is the answer. Okay, to put it simply, oxygen does not have vacant d orbitals, whereas sulfur has vacant d orbitals. Now let us discuss this a little bit in detail, revising what we have learned in the previous class. So in the previous class we have discussed about oxygen, and I am showing only the outermost shell. So I am showing here 2s and (2p). Oxygen has 2s completely filled and 2p it has 4. There is no possibility of having 2d orbitals. There are no 2d orbitals. It's not possible. So oxygen has no vacant d orbitals. Okay? Oxygen has no vacant d orbitals. It is not possible. However, in case of sulfur, as we saw in the last class, sulfur starts out just like oxygen, having 3s and 3p, which is exactly the same as oxygen in the same manner. However, sulfur has vacant 3d orbitals. 3d orbitals are possible, they do exist, and they are not filled, they are empty, vacant. In the first excited state, this being the ground state, in the first excited state, when we give energy to sulfur, the electrons in 3s will remain, but the electrons in 3p will jump to, one of the electrons will jump to 3d, thus making 4 orbitals available, 4 vacant or 4 actually half filled orbitals, where they are unpaired electrons which can overlap and form 4 chemical bonds. Okay, so it can form 4 bonds, but if we further excite it, if you give a little bit more energy and you further excite it, so I'm writing the second excited state, even this electron from here would jump to here and we will have 6 unpaired electrons. So we can have 6 bond formations, and that is why we can see that something like SF6 can form. In SF6 what happens? In SF6 we can say that there is what, 1s bonded with 6 fluorine atoms, which is possible here because there are 6 unpaired electrons, so 6 orbitals can overlap and form SF6. However, oxygen, there are no vacant d orbitals. Since there are no vacant d orbitals, we cannot have something like OF6. At best we can have is something like OF2, which exists. So this is the reason, the vacant d orbitals, the absence of vacant d orbitals is the reason why OF6 does not exist. Rather, SF6 can exist because there are vacant d orbitals in which with the electrons can be excited into, and we can have 6 unpaired electrons which can form bonds with 6 fluorine atoms and form this SF6. We can also have an SF4, as we saw. We had before in the second excited state. In the first excited state there were 4 unpaired orbitals, unpaired electrons, so we can have SF4 as well. Okay, so this is the different oxidation states that sulfur can show. Sulfur can show higher oxidation states, oxygen cannot show though. Okay, and one more thing I would like to talk about the oxidation states is that, as you can see here, SF6, this does not exist, of course, OF6, but in OF2 oxygen is actually showing a +2 oxidation state because fluorine is even more electronegative than oxygen. Who is more electronegative than oxygen? Fluorine. But there isn't anybody else who is more electronegative than oxygen, so oxygen will not show positive oxidation state with any other element. If it forms compounds with any other element, it will not show positive oxidation state, only with fluorine. However, sulfur is not so electronegative, and as we go down it is even less. Selenium and tellurium, they are even less electronegative, and they can show positive or negative oxidation states depending upon with whom they are forming the bond. Okay, so that is related to the oxidation states and related to the existence of SF6 and OF6, which does not exist, and SF6 which does exist. Let's move on to the next question. That is the atomicity. Let's talk about the atomicity. Atomicity of the molecules of sulfur and oxygen. Now oxygen is diatomic. And sulfur is octatomic. Okay, even selenium can be octatomic. So oxygen is diatomic, sulfur is octatomic. What is the reason? What do you mean by, first of all, diatomic and octatomic? We have seen that oxygen is always we write oxygen molecule as O2. Sulfur we write as S8. 8 atoms of sulfur are coming together to make a molecule of sulfur, whereas two atoms of oxygen are coming together to form a molecule of oxygen. Okay, so why is that, and why is that only here is O2 and there is S8? We will discuss this now. So now we are discussing the reason behind the difference in atomicity of oxygen and that of sulfur. Oxygen is O2, sulfur is S8. Why is that so? The reason here again lies in the structure of these two. First of all, oxygen atom is very small. Oxygen atom is very small compared to sulfur. It is having less atomic radius. Atomic radius oxygen is very less. Atomic radius of oxygen is very small. Very small. So what happens because of the small atomic radius, the overlap between the orbitals, there can be two types of overlap between the orbitals, the sigma bond and the pi bond, right? Sigma is head to head overlap and pi is side to side, is it not? Side to side overlap. So in this case what happens, there are two p orbitals, right, having unpaired electrons, one electron unpaired. So what happens in this case of oxygen is, oxygen, the p orbitals can overlap, okay, can overlap head to head forming a sigma bond, and then the remaining p orbital having one electron, the single electron each, they can overlap effectively sideways. Lateral overlap can be very effective. They can form p pi bonds. That means they can form p and p orbitals can overlap and form pi bonds. Sidewise overlap can be effective. Okay, this head to head overlap and side to side overlap, so they are forming double bond. The oxygen double bond is very stable. Okay, oxygen double bond is very stable, and that's why they form O2 as a molecule. However, that is not the case in sulfur. In sulfur what happens? In sulfur what happens? The bond length is quite large. The sulfur-sulfur single bond, the length is quite large. The radius, the atomic radius of sulfur is quite larger than oxygen, and because of that sulfur-sulfur bond length also is quite large. Because of this large bond length, and the pi bonding is not sufficient. The p orbitals that are left unpaired, they cannot do sufficient overlapping. The overlapping is not quite strong, so sulfur-sulfur double bond is not very strong. It's not very stable, not very strong. Why so? Because of the bond length basically. So the atomic radius is very large, so the head to head overlap is fine, but the side to side overlap is not as effective, so double bonds cannot form as effectively. And as a result, what happens? Instead of forming double bond with one sulfur, they will form another single bond with another sulfur, and like that it will go on till they form the structure of sulfur, that is S8, the puckered structure of sulfur. We're coming to that, but not now. So it can form S8 structure. So now that we have done discussing about atomicity, we will discuss about the next topic, that is, there's a question that I want to discuss is O2, oxygen, is a gas at room temperature, but sulfur is a solid. Okay, sulfur is a solid. We can also write S8, sulfur is a solid. So the thing is, the previous question about monoatomic and octatomic can come here also. How can it be discussed here? See, oxygen molecule O2 is very small. So due to its size, as we know, van der Waals forces van der Waals force depends upon the size of the molecule. Since O2 molecule is very small, the van der Waals force between the O2 molecules is also very small. As a result, the oxygen molecules, they are not so strongly attracted to each other, and hence they exist as gas at room temperature, even at higher temperatures. And we need a lot to cool it down. Even if you cool it down, we need to cool it down a lot in order to make it a liquid, because the force of attraction between the oxygen molecules is not very strong. Why is it not very strong? Because van der Waals force depends on the size of the molecules, and the size of oxygen atom is quite small. Now sulfur, on the other hand, S8 molecule is quite large. Being large, the attraction forces, the forces of van der Waals forces of attraction between sulfur atom and another sulfur molecule and another sulfur molecule is very strong. Okay, so comparatively very strong. So as they are bigger, their more van der Waals forces are more, and they stick together and they exist as solid at room temperature. Okay, that is the reason. Moving on. Let us discuss now the hydrides. Hydrides of group 16 the hydrides of group 16 elements. What do I mean by hydrides? What do I mean by hydrides? Obviously, the compound with hydrogen of each and every element of group 16. Let us see who they are. We have first H2O, then we have H2S, then we have H2Se, and finally we have H2Te. Okay, so we will discuss several things about this. We will discuss their acidic character, we will discuss their bond angles, we will also discuss their melting point and boiling point. Basically, we will discuss their volatility, which means melting point or boiling point. Okay, here in this case, boiling point basically. So we'll discuss these things one by one about the hydrides of group 16 elements. So let us start with the very first property, that is acidic character. So let us discuss right now the hydrides of group 16 elements, and the first thing that I'd like to discuss about them is the acidic character. So as we know, water is considered to be neutral. But what about the next? We also know that H2S is an acidic gas. Is it not? Then there is H2Se and H2Te. We don't know about them right now, still now. Let's discuss what happens to the acidic character. What has been found out is that the acidic character actually increases down the group. Acidic character acidic character increases down the group. As we move from H2O to H2S to H2Se and H2Te, as we are going down, the acidic character of each of these molecules is greater and greater and greater. It increases. Why does it increase? Let's find out the reason. The reason here actually is, the bond length and bond dissociation enthalpy. Let me discuss this in detail. See, bond length. What do we know about bond length here? We know down the group the atomic radius is increasing. Oxygen is the smallest, sulfur is larger, selenium is larger, tellurium is even larger. As the atomic radius increases, so does the bond length. The OH bond length is smaller, the SH bond length is larger, the H and Se bond length is larger, and so on. So as the bond becomes larger and larger, the bond length becomes longer and longer, it becomes weaker and weaker actually. It is easier to break. The bond dissociation enthalpy required is less. What is required less? The bond dissociation enthalpy. Bond dissociation enthalpy. That is actually the energy required to break these bonds becomes lower and lower as we go down the group. So why does that matter? What will happen then? If the bond dissociation energy is less, that means this bond can break. If this bond breaks, what will be released? H plus will be released. So whoever can release H plus, proton, hydrogen ion, whoever can release H plus more easily is more acidic in character. Okay? Whoever can release H plus more easily is more acidic in character. So because of that, as the bond lengths get larger and larger, as we move down the group, the bond dissociation enthalpy becomes lower and lower. It becomes easier to break the bonds. And as it becomes easier to break the bonds, it is easier to release H plus. So as it is easier to release H plus, the lower we go, the more acidic character they show, they exhibit. Okay? So if I write the order of the acidic strength here, what will be the order? The order will be H2O is the least, then will be H2S, then will come H2Se, and then will come H2Te. Okay? That is the strength of acidic character trend, the increasing order down the group. Okay. Then next we'll talk about the bond angles.